What if the most massive structures in our universe are completely invisible, and the data they are generating is currently breaking the fundamental laws of physics we rely on? In the observational data extracted from a gravitational lens situated 10 billion light-years from Earth, astrophysicists have detected a geometric impossibility. A structural anomaly possessing the mass of 1 million suns is actively warping the fabric of space-time, yet it emits absolutely zero electromagnetic radiation across any detectable spectrum. To comprehend the sheer magnitude of this spatial violation, we must first ground ourselves in the foundational mathematics of Albert Einstein's general theory of relativity. Published in 1915, this framework posits that gravity is not a Newtonian tether pulling objects across a static void, but rather a dynamic curvature of spacetime itself. Mass deforms the geometric grid of the universe. Consequently, when photons of light traverse the cosmos, they are forced to follow these gravitational depressions. If a massive foreground structure aligns perfectly between our terrestrial observatories and a distant luminous source, the foreground mass acts as a cosmic magnifying glass. It bends, smears, and focuses the background light into an optical phenomenon known as an Einstein ring. The specific gravitational lens at the epicenter of this cosmological crisis is designated JVAS B1938+666. Located in the directional vector of the constellation Draco, the geometry of this system is mathematically exquisite. We are observing a massive elliptical foreground galaxy, whose photons have been traveling for 8 billion years, perfectly occluding a background galaxy situated over 10 billion light-years away. For decades, this system was catalogued merely as a textbook demonstration of relativistic optics. However, in 2012, astronomer Dr. Simona Vegetti hypothesized a revolutionary metric. If the mass distribution of the foreground lens was completely uniform, the resulting ring of light would be geometrically flawless. But if an invisible localized mass concentration, a subgalactic clump, were embedded within the lens, it would induce immeasurable perturbation in the arc of the light. By analyzing the topological imperfections of the ring, scientists could effectively weigh the invisible. To detect a spatial perturbation of this minute scale requires an optical resolution that defies conventional engineering. The solution was very long baseline interferometry, or VLBI. By synchronizing a global network of radio telescopes utilizing atomic clocks, astronomers synthesized a singular, planet-sized aperture. When a research team led by Dr. John McKean directed this Earth-spanning instrument toward JVAS B1938+666, the resulting data yielded the highest fidelity interferometric map ever generated of the system. And within that pristine dataset, there was a critical flaw, a localized distortion, a pinch in the relativistic arc exactly indicative of a hidden gravitational anchor. Through rigorous computational modeling, Dr. Vegetti's team isolated the gravitational signature of this specific anomaly from the macroscopic lensing effect of the host galaxy. The mathematical output was staggering. The invisible entity weighed approximately 1 million solar masses. It was the lowest mass dark object ever detected at such a profound cosmological distance. By every direct method of electromagnetic observation, this object does not exist. It registers no infrared thermal signature, no radio frequency emissions, no X-ray scattering. It is a million solar masses of absolute nothingness, detectable solely through its localized gravitational tyranny over the surrounding spacetime metric. The most statistically probable explanation would classify this entity as an ultra-faint dwarf galaxy, a structure composed predominantly of dark matter with a negligible stellar population. To understand why this easy answer catastrophically fails, we must examine the historical architecture of the missing mass problem. Since the 1930s, when Fritz Zwicky documented anomalous velocity dispersions in the Coma cluster, and later in the 1970s when Vera Rubin analyzed the extreme rotational velocities of spiral galaxies, empirical data has mandated the existence of an invisible gravitational scaffold. We call this dark matter. The prevailing cosmological consensus is anchored by the cold dark matter, or CDM model. In this framework, dark matter consists of non-relativistic, weakly interacting massive particles that aggregate into vast spherical halos. These halos dictate the formation and structural integrity of all observable galaxies. Crucially, the mathematics of cold dark matter make highly specific, rigid predictions regarding the density profiles of these halos. According to standard thermodynamic simulations, a dark matter clump of 1 million solar masses must distribute its mass following a precise, gradual gradient. It should be relatively diffuse, lacking a highly concentrated core. Herein lies the catastrophic data point that is currently fracturing our cosmological models. When Dr. David Massari and the research team reconstructed the internal mass distribution of the anomaly within JVAS B1938+666, they discovered that it explicitly violates the density parameters dictated by the cold dark matter model. The object is not a diffuse, uniform cloud. It possesses a hyperdense, ultra-compact core that accounts for roughly 25% of its total mass, surrounded by an abnormally extended spatial halo. Its internal architecture is a structural hybrid, something suspended between the metrics of an ultra-compact stellar system and a diffuse dark matter subhalo. By the established laws of standard particle physics, a dark matter clump of this specific mass parameter simply cannot compress this much material into such a restricted volumetric space. In empirical science, a single anomalous data point can often be dismissed as a statistical artifact or an instrumental calibration error. However, a recurring anomaly signifies a paradigm collapse. Astrophysicists have recently subjected another gravitational lens, designated SD/SSJO946+1006, colloquially known as the jackpot lens, to similar interferometric scrutiny. The subhalo detected within the jackpot lens exhibits the exact same structural impossibility. It is exponentially more concentrated than the cold dark matter framework permits. Multiple independent research teams utilizing divergent computational methodologies have arrived at the identical, uncomfortable conclusion. We now possess a repeating pattern of hyperdense dark objects that mathematically refuse to align with the foundational theory of how our universe is constructed. Faced with this systemic failure, theoretical physicists are being forced to entertain hypotheses that fundamentally rewrite the laws of the dark sector. The first alternative framework is self-interacting dark matter, or SIDM. In the standard model, dark matter particles are strictly collisionless. They pass through one another like phantoms, interacting solely via gravity. But under the SIDM paradigm, these particles possess the capacity for kinetic exchange. They can collide, scatter, and transfer thermal energy. Over cosmological timescales, these thermal interactions can trigger a localized thermodynamic collapse, causing the core of the dark matter halo to contract and spike in density. The hyperdense core observed in JVAS B1938+666 perfectly mirrors the mathematical simulations of a late-stage core collapse in a self-interacting dark matter framework. An even more radical proposition is the framework of fuzzy, or wave, dark matter. This hypothesis posits that the dark sector is composed of ultralight, axion-like particles with masses so infinitesimally small that their quantum mechanical wavelengths stretch across macroscopic distances. In this scenario, dark matter behaves less like discrete particles and more like a fluid field of quantum waves. The hyperdense core we are observing would not be a physical clustering of particles, but rather a soliton, a self-reinforcing, standing quantum wave anchored at the gravitational center of the halo. There remains a third, equally disruptive possibility that has permeated astrophysical discourse: the extreme central density could indicate the presence of a supermassive or primordial black hole serving as the gravitational anchor for this dark subhalo. If a black hole of substantial mass were deeply embedded within this structure, it would easily account for the intense central concentration of mass. However, the existence of such a massive black hole within a relatively low-mass subhalo at a distance of 10 billion light-years would require a complete revision of our models regarding early universe black hole formation and galactic evolution. Every single theoretical explanation for this anomaly demands that we discard a significant portion of our established cosmological knowledge. We are currently operating at the absolute threshold of human observational capability. The entire theoretical foundation of modern astrophysics now hinges on a single, upcoming observational metric. The James Webb Space Telescope is now tasked with targeting the exact spatial coordinates of this gravitational distortion to search for the faintest thermal signature of stellar populations. If this unprecedented instrument analyzes a confirmed concentration of 1 million solar masses and registers absolute, uncompromising darkness, we will have to abandon a century of standard physics and accept that the dominant force shaping our cosmos is a completely unrecognized state of matter. If the James Webb Space Telescope detects even a marginal flux of infrared photons, the cosmological crisis softens considerably. Such a detection would reclassify the anomaly as an ultra-faint dwarf galaxy. It would still represent an extreme astrophysical environment, an awkwardly massive and unusually concentrated dark matter halo anchoring a severely underpopulated stellar component. But it would remain a galaxy. It would be a structural outlier, yet one that can be forced into the parameters of current baryonic physics. However, the absence of an emission spectrum changes the fundamental nature of the inquiry. If a structure containing the mass equivalent of 1 million suns, precisely localized in spacetime, emits zero infrared radiation, we are forced to eliminate baryonic matter as a significant component. The James Webb Space Telescope is not merely a large optical instrument. Its gold-coated beryllium mirrors and cryogenic operational temperature at Lagrange point 2 make it the most exquisitely sensitive infrared detector ever engineered by our species. It is specifically calibrated to capture the highly redshifted ancient thermal signatures of the early universe. If an instrument of this unprecedented caliber stares directly into the spatial coordinates of this gravitational distortion and registers absolute, uncompromising darkness, this would confirm the entity is composed almost entirely of a dark sector material that refuses to interact electromagnetically. Combined with the mathematically anomalous density gradient we have already measured, this absolute absence of luminosity would officially categorize the entity as a completely novel class of astrophysical object. It would not fit the cold dark matter paradigm due to its extreme central concentration, and it would not fit the classification of a low surface brightness galaxy due to its total optical and infrared silence. Within the rigorous framework of the scientific method, an observational null result, finding an absolute void where theoretical models mandate the presence of matter or energy, is often the most potent catalyst for paradigm shifts. The epistemological value of an empty dataset in this specific context cannot be overstated. If the standard cosmological model is accurate, baryonic matter must be present in a mass concentration of this magnitude. If baryonic matter is unequivocally absent, the model is fundamentally incomplete. We are currently suspended in a state of observational superposition, awaiting a singular dataset that will either stretch our existing theories to their absolute breaking point or shatter them entirely. The distinction between a faint glow and absolute darkness in this singular patch of the Draco constellation will dictate the future trajectory of theoretical physics. Regardless of the final spectral analysis of this specific anomaly, the interferometric methodology that isolated it is on the verge of an unprecedented technological scaling. The detection within JVAS B1938+666 was a painstaking, highly localized triumph. The culmination of years of data processing focused on a singular gravitational lens, pushing terrestrial radio arrays to their theoretical resolution limits. By synchronizing radio telescopes across multiple continents, astronomers synthesized an effective aperture the size of the Earth, achieving sub-milliarc-second angular resolution. But observational astrophysics is currently undergoing a massive infrastructural transition. We are shifting from isolated, serendipitous discoveries to systematic, wide-field statistical surveys. The European Space Agency's Euclid Observatory, engineered specifically to map the geometric expansion and structural evolution of the dark universe, is projected to identify hundreds of thousands of new gravitational lenses. This represents an exponential increase from the few hundred confirmed lensing systems available in our current catalogs. Each of these newly identified optical distortions serves as a potential laboratory for probing dark matter substructures. Concurrently, the Square Kilometre Array, a transcontinental radio observatory currently under construction across Africa and Australia, will provide the interferometric baseline required to resolve these lensing anomalies with unprecedented precision. The localized spatial distortion we are currently analyzing is not an isolated curiosity. It is the statistical precursor to a massive influx of high-resolution gravitational data. We are about to transition from studying individual anomalies to cataloging a vast, invisible taxonomy of dark structure. To comprehend the gravity of this methodological shift, we must contextualize it within the broader 90-year crisis of modern physics. The dark matter problem remains the most glaring deficiency in our understanding of the material universe. The crisis first materialized in the 1930s when astrophysicist Fritz Zwicky measured the velocity dispersions of galaxies within the Coma cluster and calculated that the visible mass was insufficient to prevent the cluster from flying apart. Decades later, Vera Rubin's exhaustive analysis of galactic rotation curves confirmed that the stars at the extreme edges of spiral galaxies were orbiting at velocities that blatantly violated Newtonian dynamics based solely on luminous mass distributions. Observational kinematics dictate that we are living in a cosmos where luminous matter is merely a superficial contaminant. By integrating the velocity dispersions of galactic clusters, the rotational curves of spiral galaxies, and the temperature fluctuations of the cosmic microwave background, we have rigorously quantified the mass-energy density of the universe. The data is mathematically unambiguous. Approximately 85% of all matter in the universe is fundamentally invisible. Every stellar ignition, every planetary accretion disk, every nebula emitting across the electromagnetic spectrum, these represent a fractional minority of the cosmic mass budget. We inhabit a universe dominated by an invisible, massive substrate, yet after nearly a century of theoretical and experimental labor, the fundamental particle physics of this substrate remains completely unknown. We have never isolated a single dark matter particle within a controlled laboratory environment. We have never recorded a non-gravitational interaction between the dark sector and the standard model of particle physics. It remains the most massive component of the physical universe, yet it exists solely as a mathematical ghost in our kinematic equations. For decades, the primary vector for resolving this crisis has been the direct detection paradigm. Deep within subterranean facilities, shielded from the background noise of cosmic ray muons by thousands of meters of solid rock, physicists have constructed the most sensitive thermodynamic and scintillating instruments in human history. We have deployed massive cryogenic vats of liquid xenon and arrays of ultra-pure germanium crystals, chilled to fractions of a degree above absolute zero. The operational hypothesis relies on the assumption that as the Earth traverses the Milky Way's dark matter halo, we are constantly bombarded by a flux of weakly interacting massive particles. The expectation was that given a sufficient target mass and adequate time, a dark matter particle would eventually undergo an elastic scattering event with a baryonic nucleus, depositing a measurable quantum of kinetic energy, a microscopic flash of light, or a transient thermal spike. For over 30 years, these operational parameters have been scaled up. Detector volumes have increased exponentially, and background rejection algorithms have achieved unprecedented precision. Yet, the empirical output of these multi-million-dollar subterranean arrays has been absolute, uninterrupted silence. No confirmed detection of a dark matter particle has ever been recorded. The theoretical candidates favored by supersymmetry and high-energy particle physics, which were confidently predicted to materialize within the collision parameters of the Large Hadron Collider, have completely failed to appear. The direct search for dark matter, conducted with the most precise physical instruments humanity has ever engineered, has returned nothing but null datasets. Against this backdrop of persistent experimental failure, the gravitational lensing approach represents a crucial, paradigm-altering methodological pivot. We are no longer relying exclusively on the highly improbable hope of capturing a singular microscopic particle interaction in a subterranean tank. Instead, we are interrogating the macroscopic morphology of the dark sector using the only fundamental force it reliably responds to: gravity. Rather than asking the binary question of whether dark matter exists, a fact already confirmed by macroscopic cosmic geometry, or attempting to quantify its total mass fraction, we are now asking a far more sophisticated structural question. We are analyzing the specific spatial distribution of dark matter when it aggregates into subgalactic halos. By measuring the precise density gradients, the radial concentration indexes, and the internal mass distribution of these invisible clumps, we can actively differentiate between competing particle physics models on a cosmological scale. If the internal geometry of a subhalo exhibits an extreme central density that violates the collisionless assumptions of cold dark matter, we are theoretically compelled to introduce self-interacting cross-sections into our particle models. If the subhalo core exhibits the mathematical signature of a quantum soliton, we must elevate the fuzzy, wave-like dark matter hypothesis from a mathematical curiosity to a leading astrophysical model. For the first time in the history of cosmology, the detailed internal structural mechanics of invisible matter, rather than just its aggregate gravitational pull, are becoming a directly observable metric. We are transitioning from merely weighing the dark universe to actively mapping its internal anatomy. The Draco anomaly is not just an isolated structural failure of the Standard Model. It is a critical data point in the ongoing effort to classify the fundamental nature of reality. It forces us to confront a severe observational bias that has defined astronomy since antiquity. Historically, the discipline of astronomy has been entirely defined by the detection and analysis of electromagnetic radiation. We have constructed our entire cosmological framework based on the behavior of photons. The universe we have mapped is the luminous universe, a universe of things that shine, radiate, and emit thermal signatures. But the object distorting the Einstein ring in JVAS B1938+666 fundamentally rejects this methodology. It emits 0 photons across the entire electromagnetic spectrum. It was detected, quantified, and structurally modeled purely through its geometric deformation of local spacetime. It serves as a stark, empirical reminder that the luminous universe is merely a thin, glowing veneer draped over a vastly more massive, fundamentally dark architecture. The stars and galaxies we observe are not the structural foundation of the cosmos. They are merely the visible tracer particles trapped within the gravitational wells of a much larger, invisible reality. We have spent centuries studying the lights, assuming the darkness between them was simply empty space, a passive vacuum serving as a backdrop for baryonic physics. The high-resolution interferometric data now confirms that this assumption was catastrophically flawed. The darkness is not a void. It is a dense, highly structured medium that dictates the kinematic behavior of everything we can see. And somewhere within that invisible medium, 10 billion light-years from our local coordinate system, a concentration of mass equivalent to 1 million suns, is maintaining a physical structure that our current laws of physics dictate should be impossible. It sits in the deep cosmic past, casting a gravitational shadow that has traveled through the expanding vacuum of space for longer than our solar system has existed, waiting for our instrumentation to evolve enough to perceive its distortion. The chain of physical inference required to even recognize its existence necessitates a level of technological and mathematical precision that borders on the absolute limits of human capability, forcing us to ask what other invisible monoliths are currently warping the fabric of space-time just beyond our field of view. To empirically resolve this localized gravitational anomaly, the observational matrix must shift from radio interferometry to the deepest infrared regimes accessible to our current technological infrastructure. The James Webb Space Telescope represents the ultimate arbiter in this diagnostic process. If this mass concentration is merely an ultra-faint dwarf galaxy, it must possess a baryonic component. Even the most suppressed star formation history would yield a residual population of low-mass stellar objects, emitting a detectable thermal signature. If the JWST directs its segmented beryllium mirrors toward the exact spatial coordinates calculated from the lensing deflection and detects a localized flux of infrared photons, the anomaly undergoes a taxonomic reclassification. It becomes a highly atypical dwarf galaxy with a disproportionately massive and centrally concentrated dark matter halo. This outcome would force a severe recalibration of galaxy formation models, requiring mechanisms to explain such extreme baryonic suppression, but it would fundamentally preserve the lambda-CDM cosmological framework. The standard model would stretch to accommodate a statistical outlier, but it would not shatter. However, the alternative outcome carries paradigm-shifting implications. If the JWST integrates its exposure over the target coordinates and registers absolute zero emission, a complete absence of baryonic radiation, the epistemological landscape of astrophysics changes instantaneously. A localized mass of 1 million solar equivalent units, exhibiting extreme central density yet devoid of even a single radiating star, cannot be reconciled with any conventional astrophysical mechanism. It would confirm the existence of a purely dark structure, a morphological class of object completely unpredicted by current theoretical frameworks. In the rigorous domain of physical science, the most profound discoveries often manifest not as novel signals, but as the sudden, deafening absence of a predicted signal. Finding nothing where the standard model demands something is the exact mechanism by which scientific revolutions are catalyzed. A null detection by the JWST would be the ultimate empirical validation that our understanding of the universe's fundamental constituents is critically flawed. Regardless of the specific baryonic threshold of JVAS B1938+666, the interferometric methodology that isolated its gravitational signature is on the precipice of an exponential scaling phase. The detection of this single subhalo was a labor-intensive anomaly, requiring years of meticulous data processing to filter out macroscopic gravitational foregrounds. But the era of singular artisanal gravitational lens analysis is ending, giving way to an epoch of systematic cosmological surveying. The European Space Agency's Euclid Observatory, engineered specifically to map the geometric evolution of the dark universe, is projected to catalog hundreds of thousands of new strong gravitational lenses. This represents a staggering statistical leap from the few hundred confirmed systems available to astrophysicists today. Each of these newly discovered Einstein rings constitutes a pristine, high-resolution laboratory for probing dark matter substructure. Simultaneously, the terrestrial observational infrastructure is undergoing a radical upgrade with the square-kilometer array. Spanning intercontinental baselines, this radio observatory will achieve an angular resolution capable of dissecting these gravitational distortions with unprecedented precision. This systematic mapping is a critical diagnostic tool aimed at resolving a 90-year-old crisis in fundamental physics. Since the initial kinematic anomalies observed in galactic clusters during the 1930s, empirical data has remained stubbornly consistent. The observable universe is structurally dominated by a non-baryonic mass component. Current cosmological parameters dictate that roughly 85% of all matter in the universe is fundamentally disconnected from the electromagnetic spectrum. Every star, planetary system, and galactic disk combined represents a mere minority fraction of the cosmos, a superficial, luminous froth floating upon a vast, invisible gravitational fluid. Yet, Despite nearly a century of observational confirmation regarding its macroscopic effects, the microscopic nature of dark matter remains a complete void in our standard model of particle physics. The historical approach to solving this crisis has been fundamentally reliant on the assumption of weak interactions. Deep within subterranean facilities, shielded by kilometers of rock from the interfering cascade of cosmic rays, experimental physicists have constructed the most exquisitely sensitive diagnostic environments in human history. They have deployed massive cryogenic tanks filled with liquid xenon and meticulously calibrated arrays of ultra-cold crystals. The operational hypothesis dictates that as the Earth translates through the Milky Way's dark matter halo, an ambient wind of weakly interacting massive particles should constantly stream through our planet, occasionally scattering off an atomic nucleus to initiate a measurable cascade of scintillation light. For over 3 decades, these subterranean direct detection experiments have systematically increased their target mass and refined their background rejection algorithms. And for over 3 decades, the empirical yield has been absolute silence. No confirmed nuclear recoil event attributable to a dark matter particle has ever been recorded. Against this backdrop of prolonged experimental null results, the gravitational lensing approach represents a profound methodological pivot. Rather than attempting to force an improbable kinetic interaction between a hypothetical dark particle and a baryonic nucleus in a localized terrestrial laboratory, this approach utilizes the cosmos itself as the diagnostic instrument. It studies dark matter through the only fundamental force by which it has ever reliably manifested: gravity. The critical inquiry has evolved into a highly refined morphological analysis. What specific geometric configuration does dark matter assume when it collapses into a localized potential well the size of a dwarf galaxy? The structural morphology of a dark matter subhalo is a direct macroscopic reflection of its microscopic particle physics. The standard cold dark matter paradigm relies on collisionless particles that naturally produce a specific, predictable density gradient. The anomaly in JVAS B1938+666 violently contradicts this gradient. If subsequent high-resolution surveys confirm that extreme central densities are a systemic feature of dark subhalos, it could provide the first empirical evidence for self-interacting dark matter. Alternatively, if the core exhibits a specific solitonic profile, it could validate the macroscopic quantum interference patterns predicted by fuzzy dark matter. The answer to the dark matter crisis may not emerge from a fleeting photon flash in a subterranean tank, but from the precise geometric contours of an invisible mass-bending ancient light. This methodological evolution forces a profound philosophical recalibration of astrophysics. Since the dawn of human observation, our understanding of the cosmos has been entirely dictated by the electromagnetic spectrum. Astronomy has, by definition, been the rigorous study of light. But the localized mass concentration distorting the Einstein ring in Draco rejects this fundamental premise. It emits no photons. It reflects no radiation. It forces us to confront the uncomfortable reality that the luminous universe is not the true universe. The true universe is a dark, massive architecture that we can only perceive through the localized gravitational shadows it casts upon the background radiation. This anomaly is a singular manifestation of that deeper reality, made briefly perceptible only because a background galaxy emitted a stream of photons 10 billion years ago. Those photons traversed the expanding metric of space, encountered the gravitational curvature of a foreground galaxy, and were warped into a perfect ring. Somewhere along that ancient geodesic path, an invisible mass exerted a microscopic gravitational pinch, permanently altering the trajectory of the light before it was intercepted by a network of terrestrial radio antennas. The chain of physical inference required to extract a mass and a density profile from that faint distortion is a testament to the extreme capabilities of modern theoretical physics. Yet, at the terminal end of that complex mathematical derivation, there remains an unresolved physical reality, We possess the precise coordinates, the mass calculations, and the structural morphology, but the fundamental identity of the object remains entirely obscured. We do not know if its hyperdense core is the gravitational signature of an intermediate mass black hole, the collapsed remnant of self-interacting dark particles, or a completely novel physical phenomenon. We do not know if the James Webb Space Telescope will ultimately resolve a faint cluster of ancient stars, or if it will stare into the designated coordinates and confirm an absolute, terrifying void. What we do know, with high statistical confidence, is that a localized mass of 1 million solar equivalents exists 10 billion light-years away, maintaining a structural configuration that breaks our current models. For millennia, humanity looked upward and assumed the night sky was a map of luminous objects suspended within an empty, passive void. The empirical data now demands an inversion of this worldview. The dark is not empty. It is overwhelmingly full. It is saturated with a massive, invisible medium that dictates the kinematic evolution of the cosmos. The stars, the galaxies, and the light we have spent centuries studying are merely the rare, glowing exceptions. The darkness is the fundamental rule. And somewhere within that vast, unlit architecture, a massive anomaly continues to hold its impossible shape, waiting for our instrumentation to achieve the sensitivity required to comprehend its nature. For those who find intellectual value in tracking these frontier anomalies, I encourage you to register your algorithmic preference by subscribing to the channel, liking this presentation, and engaging with the data in the comments. Your active participation is a critical metric that allows this specialized academic analysis to persist. The luminous universe may be a superficial illusion, but our empirical pursuit of the dark reality beneath it has only just